Greetings, this is Mr. T. This is commentary for Packet 16, Acids and Bases, Part 2. So we talked about the definitions and application of acids and bases to increase the acidity or basicity of a neutral solution. We also talked about quantitative means of measuring it. That means where we use numbers. The most famous one is pH calculations and pOH calculations. In slide 2, we summarize all of the calculations you had to learn from part 1 of the acid and base chemistry. If you haven't already, please be sure to practice using the log anti-log buttons for use in pH calculations on your computer, and make sure to use your calculator. And that means you're going to have to Google the calculator brand in order to figure out those details, because every manufacturer has their own way of doing log and anti-log calculations. Above all, you have to memorize and, well, I got messy really fast. You have to memorize and master these equations. So this is the ion product constant equation in P form. That means they took the negative log of everything. And these are the various formulas you have to memorize. You should probably also memorize that table which shows the relationship. So make sure you have all of these mastered. Make sure you understand the concepts for these. And now let's go into qualitative determinations of acid-base chemistry. So before looking at the pH, for example, we learned that if you went from 1 to 6, then that's going to be acidic. Or if you went from 8 to 14, based on the pH, that's going to be basic. And then, of course, 7 is going to be neutral. And they have special instruments such as pH meters, which measure the pH of a solution to tell you whether it's acidic, basic, or neutral. Now we're going to be looking at qualitative determinations. So we assume that we've created our acidic or basic solution by adding in an acid or base, and we need to figure out through its qualities or properties whether it's acidic or basic without actually using fancy instruments. So there's different ways that we can do this. One way is the taste test. If it's sour, then it's acidic. If it's bitter, when you taste it, it's basic. So if you were to sit there and get your mouth washed off with soap because you did something you shouldn't have said, then you would have found that soap is very bitter. Not that I ever did that, because that would be wrong. Okay, maybe I said a few words I shouldn't have, and so I've eaten a lot of soap in my lifetime. Alright, sour, such as soda, is going to be sour. There's certain candy that has a sour taste, and it's acidic. Field test. Highly recommend you don't do this, but if you were to stick your hand in Drano, other than writhing in pain, you would find that it's slippery. Soap, because it's also basic, is also very slippery as well. They even use the term soapy. So part of the reason it slips out of your hands is because it's basic. Acidic solutions don't slip out of your hand. Litmus paper. Now we have these various red and blue litmus papers that we can go ahead and use our dropper to put a couple drops of our unknown solution on there to figure out whether it's acidic or basic. So in short, blue litmus paper turns red when it's acidic. That's supposed to be blue, but it's purple. Just work with it. And then red turns blue when it's a basic solution added. You can go by pH litmus paper. pH litmus paper is really cool because based on what color it turns, then you'll be able to figure out what the pH is. You could also use a pH meter, which is an instrument which measures it. So for example, if I had a purple solution, then maybe that purple solution equals a pH of 9, for example. Whereas if I had a red solution, maybe it was a pH of 1. So they call those universal indicators. And if you take any more science, then you'll be messing around with those. And then we can do a neutralization reaction. Usually we have to do this with strong acids and bases. So we'll get into what those are. But as an example, if I have hydrochloric acid and I had some unknown beaker and I didn't know what it was, then I could sit there and mix that hydrochloric acid in there. And let's say the unknown is actually a base, such as sodium hydroxide. So if I mix the known acid with an unknown base, then I should end up with a neutralization reaction, where all of the hydroniums are neutralized with the hydroxides, creating a neutral solution of sodium chloride and water, for example. So for acidic solutions, by adding a strong base, then it will produce a salt and water. If I'm dealing with a basic solution, then by adding an acid, then it creates salt and water. It's helpful to know what is strong versus weak acid and bases, and we'll get into that shortly. I need you to memorize these different qualities. And now we're going to get into something called indicators. Now, I made a indication to, no pun intended, to a special type of litmus paper which has different types of colors that are generated based on the pH. Well, we also have liquid indicators, and by adding a liquid indicator to our solution based on the color change, then we know what the pH is, our relative pH it is. So methyl red produces these various colors indicating the crude pH. Bromothymol blue creates these different colors. Please keep in mind, based on the pH, it may not look blue, it may look yellow, for example, or if it's neutral, it may look clear. And the most popular indicator, especially we'll use it in acid-base titrations, if I have a pH of 2 all the way up to 8, it's going to be clear. And then if it's from 9 above, then it's going to be pink. So what do you need to do? You need to memorize this table right here. Methyl red, bromothymol blue, and phenolphthalein. Memorize the names. Make sure you can spell them properly. Memorize the cutoff for the color changes. So for example, below a pH of 5, then methyl red will be red. Above a pH of 5, it will be yellow. For bromothymol blue, if it's below 7, it's yellow. Above 7, it's blue. And phenolphthalein will be colorless below 9 and pink above it. So make sure you have this memorized. We love using these universal liquid indicators or acid-base indicators, same thing, when we do titrations for endpoint analysis. What is endpoint? We'll get into that a little bit later. So it's video time. We have an indicator there.
Ice to water. First, we add bromothymol.
Excuse me. Even though it looks green, it's actually bromothymol blue. We're going to add in water here. Now, we're then going to add in dry ice. Dry ice is carbon dioxide, and what happens is it reacts with water, forming carbonic acid. The name speaks for itself. It's an acid. So before we do that, we'll just add in an indicator, and you'll notice it's not an acidic solution until we add in the acid-forming carbon dioxide.
A blue indicator to water that has been made slightly basic.
So as you can tell, based on the blue color, it falls in a pH range, making it basic. Now we're going to add in dry ice. The dry ice actually turns the water into an acid. And it creates a lot of cool bubbles. If you have any kids, that's so much fun to play with, provided it's in a safe, natural environment where you have an established instructor doing the experiment, because otherwise that would be wrong. So, as you can tell, the dry ice, aka carbon dioxide, formed carbonic acid, and it made the solution very acidic. Notice the color change. Based on the table that you have memorized, then it's safe to say that the pH is below 7 because it is acidic, based on the yellow color, having memorized the indicator table that you see in front of you. Alright, let's go back to the video. Now they're going to go ahead and add in sodium hydroxide. It's going to neutralize the acid and make it basic. So what do you think will happen to the color change? Boom, it turned blue. Yay! And I can play with these all day. So that's, now it's basic again. Now we're going to be mean and make it acidic again. By having the dry ice turn it into an acid, and it goes back and forth. Let's move on. I'm having a lot more fun. I apologize. This is something you can do at home. Yes, I said those words. You can do at home. I'm going to create a natural indicator. It's not one of the ones that you had to memorize. The natural indicator is given off by red cabbage. Now, so if you like red cabbage, then make sure to keep some of the cabbage juice after you boil it for a while. So this person is pouring out cabbage juice that has been boiling, putting them into test tubes, and these natural indicators will obviously change color depending on whether you add an acid or base to them. Again, you can actually do this at home. You'd probably want to add in soda, for example, or club soda. That would be your acid. Maybe add in soapy water as a base, lemon juice for an acid. You can do that as well. So going back just a bit, they added in sodium hydroxide. That's a base. So for this indicator, it turned it slightly green. I'm not going to tell you the name of the indicator because I don't want to overwhelm you with all these extra names. Since this is not something that you have to memorize, there's an acid, and there's going to be another color change. But you can add in various types of foods that are naturally acidic or basic, and you'll see these color changes. Pretty cool. Now we're going to get into strong versus weak acids. Now the term strong and weak has nothing to do with the concentration of the acids and bases. It has to do with whether it completely ionizes or not. So let's go back in time and visit strong and weak electrolytes so we can see where the term strong and weak came from. So this is solid sodium chloride. When put in water, all the sodium chlorides, they completely dissociate. So there's a sodium chloride. All of these sodium chlorides are trapped in solvent cages. Remember that term. And the sodium chloride is completely dissociated. Let's see that one last time. So all the sodium, which is in silver, and then chloride in green, completely dissociate. So they all turn into ions. This is a strong electrolyte. Consequently, it conducts electricity quite well, so there's a strong light that appears. Let's move forward. Now there are some species that don't turn into ions, such as sugar. They don't form ions, so therefore no electricity. So that's a non-electrolyte. So let's apply this to acids. You're looking at hydrogen chloride gas. It's not in water yet. Um, it's, it's actually in gas form. This stuff is so dangerous. So do not do this at home. So if you have any spare bottles of hydrogen chloride, gas containers floating around, yeah. Um, so anyways, this is an example of a strong acid. So let's prove it to you. First thing we do is we go ahead and get a beaker full of water. I'm just going to fast forward. There's a person putting a, filling up a beaker full of water. And then notice we have the same closed circuit light bulb in there. And then they're going to go ahead and turn on the hydrogen chloride gas. And as you can tell, as it lights up, that's because all of the gas particles are turning into ions. The hydrogen chloride are completely separating into ions. Because it's a 100% dissociation, they call it a strong acid. And you can tell it conducts electricity really good since they're all 100% ions. Now let's go forward a bit. That's acetic acid that they're going to put in. Not all of them turn into ions. So it's a weak electrolyte, ergo a weak acid. And it's indicated by the weakly shining light. Now I showed you this video before, but now we're going to be focusing on the strong and weak acid components. So there's hydrochloric acid being put in. So it doubles as a Arrhenius and Bronsted-Lowry acid. But notice how it completely ionizes, meaning it separates into ions. It doesn't come back together. And for every hydrochloric acid molecule that I put in there, they're all going to separate into ions. Because it's a strong electrolyte, we also call it a strong acid. So let's do another one. This is nitric acid. We go ahead and we put that in. Because they 100% ionize, they don't come back together. It's a strong electrolyte, ergo a strong acid. And then this is acetic acid. Looks kind of like a horsey. A hydrogen comes off. And what happens? It goes back on. So this is a weak electrolyte. And furthermore, a lot of molecules, they won't even ionize during those brief times. They'll just stay as in their neutral form. Other ones, they'll ionize for brief periods of time, and then they'll come back together again. So let's see that again. That was kind of cool. It donates a hydrogen, and then it comes back. So that's a strong and weak acids. Now let's look at strong bases. I'm just going to fast forward this a bit. So sodium hydroxide, potassium hydroxide, those are all strong bases. Why? Because when you stick a bunch of them inside water, they all completely dissociate, aka ionize. 100% ionization. They never come back together. Don't forget, they're actually surrounded by water molecules in what's known as a solvent cage. Solvent cage. So it's a strong base because it's a strong electrolyte. This is ammonia. Ammonia and other molecules like hydrogen fluoride, they're also known as weak electrolytes. Notice how they give off a hydrogen. I'm sorry, they take a hydrogen and then they give it right back. They take a hydrogen and it gives it right back. So that's a weak base, aka a weak electrolyte. And furthermore, not all of the ammonias will actually take a hydrogen. Some of them will just stay in their neutral form. But the ones that do can take a hydrogen and then give it back. So that's a Bronsted and Lowry base. So I spent a lot of time on these setting this up and on this animation. As you can tell, you will most likely be tested on this. Shocker. So make sure you understand the definitions. Strong acids and bases, all molecules completely ionize. Weak acids and bases, some molecules ionize, others may not. They may do that partial ionization and they may change their mind, and as soon as they're ionized they may come back together again, or deionize. So now for everybody's fun part, memorize. You have to memorize the tables below and the examples from the syllabus. Let's start with this table. So these are all the strong acids and their names. Whenever we have a molecule which will function as an acid and be put into water, so all of these are going to be considered aqueous, we call them acids. And on this table, if you are one of these fortunate 6, then these are called strong acids. Now you can't just look at it to figure out whether it's strong or weak. There is no trick there. The trick is actually memorizing the table. So, hydrochloric acid is a strong acid. Hydrobromic acid, strong acid. Hydroiodic acid, nitric acid, perchloric acid, and sulfuric acid. Memorize. Here's the trick. If it's not on this table, then automatically it's going to be a weak acid. So if I have something like this, H2SO3, this is known as sulfurous acid. And because it's not on the table, it's automatically going to be weak. Now let's go down to strong bases. The names are classic names of ionic compounds that you've already learned, so I didn't write the names on here. This one right here is lithium hydroxide. This one right here is sodium hydroxide. So you should be able to reason out the names, unlike the acids. Good news, you have to memorize all of these. And if they are not on the table, you can automatically assume it's going to be a weak base. So for example, lithium hydroxide, that's going to be a strong base. Why? Because it's on the table. Magnesium hydroxide is going to be a weak base. Why? Because it's not on the table. So you should know this. You should be able to identify whether it's an acid or base, and whether it's a strong acid, strong base, weak acid, weak base. Here's another hint. Usually there's a hydrogen that's in front, indicating that it's going to be an acid, and that's the hydrogen that likes to come off. So, and they tend to be a hydrogen in front and then a non-metal at the end. Usually they're halogens, but they can also be other types of polyatomic ions. Compare that one to bases, where they tend to be a metal up in front rather than a hydrogen. And then for strong bases, you'll have a hydroxide at the very end. Now, weak bases are a little bit more challenging. Some of them are straightforward, like the magnesium hydroxide. Other ones you have to memorize. So ammonia, that is a weak base. And the only way you'd know that is to listen to the commentary and have it memorized. Sodium fluoride, this is also a weak base. First off, you know it's a base, or a potential base, because it starts off with a metal, like you see the other ones have metals. But because it's not anything on the table, you can automatically assume it's going to be a base. This is what we call a Bronsted and Lowry base, because when we put it inside water, then the fluoride will pick off a hydrogen, forming hydrogen fluoride and the brand new hydroxide. So that's a Bronsted and Lowry base. We have many types of weak bases. Sodium fluoride, for example, sodium acetate, sodium perchlorate. So many different ones. Now, let's go to the syllabus. Scroll down all the way to the back of the syllabus. Right where you have the lists of polyatomic ions and transition metals, all of which you should have everything memorized so far on this whole page now. Now, if you look to the right, here are examples of strong and weak acids that you have to memorize. Now, the strong acids are the same acids that you found in the slides, so that's no different. The weak acids, they're different. You have to memorize the name and the formulas. Now, you can still reason it out by the table, that if it's not on the strong acid table, then it must be a weak acid. But I will also test you on the names. So, for example, I could give you H3PO4, and then you have to memorize that's phosphoric acid. Or HNO2, and that's nitrous acid. Notice just by changing the number of oxygens that can change the name of the acid. And then HClO is hypochlorous acid, HClO2 is chlorous, HClO3 is chloric acid. And all of these are weak acids. Why? Well, because it's not on the strong acid table. So make sure to have those memorized. Now, let's go ahead and fast forward a bit. The next several slides talk about characteristics of strong acid and weak acid reactions and buffers. And the purpose of all of that is for slide 12. We're going to be mixing equal molarity concentrations. So for example, 1 molarity of this strong acid that I'm trying to highlight, that it won't let me highlight because it's being mean. And then 1 molarity of a strong base. So assuming they have the same concentrations, we need to figure out whether the overall solution is going to be neutral, acidic, basic, buffer, and pH varies. So if I were to sit there and put a strong acid, 1 molarity of strong acid, and 1 molarity of weak base, because acids completely ionize 100% and weak bases only partially ionize, then we'll have a lot more hydrogen ions than hydroxide. It's going to be overall acidic. On the other hand, if I have a strong base with complete ionization and a weak acid with partial ionization, we'll have a lot more hydroxides than hydroniums, and it's going to be overall basic. So the previous slides talk about these acid and base reactions, and once you've learned the principles of it, you'll apply it here and memorize the overall nature of the solution, whether it's neutral, acidic, basic, pH, and pH buffers. pH varies. Why would I do that? Because eventually I'll be asking you questions like these and say something like, assume equal concentrations of each aqueous solution. That means like 1 molarity to 1 molarity or 2 molarity to 2 molarity. Based on your understanding of what type of strong or weak acid or base it is. Is it overall nature for the aqueous solution going to be acidic, basic, neutral, neutral buffer, or pH varies? So you'll have to go ahead and put that in there. Now, I'm going to go ahead and go back here and start talking about some of these acid-base interactions. So when you mix together a strong acid and a strong base, if they have equal concentration, such as 1 molarity, then there's going to be a neutralization reaction. Neutralization reaction. Practice saying that. I know I need to. Neutralization reaction. So a strong acid, strong base, we have a neutralization reaction, and it produces a water and a salt. So for example, nitric acid, HNO3, strong acid, sodium hydroxide, strong base, that forms a salt and a water. Now, I haven't mentioned this before, but salts are going to be neutral substances. So they neither increase or decrease the hydrogen concentration or basic concentration. So they completely ignore any changes in pH. So it's neutral. Make sure you have this pattern down. Strong acid, strong base, a salt, which is a neutral species, and water. Now, this is a weak acid by itself, and as I mentioned, it likes to give off a hydrogen, and is, well, for the ones that actually donate hydrogen, some of them may not do anything at all, but the ones that donate hydrogens, it gives off a hydrogen, and then it creates a leftover ion. This leftover ion we call a conjugate. Now, as soon as it gives off the hydrogen, it can change its mind, and it can actually pick up the hydrogen once again. And we saw that in the videos. If it does that, we call it a conjugate base. A conjugate base. So here's our starting acid, donates the hydrogen, and there is the conjugate base, and it picks it up. So you'll notice we have arrows going both ways. So we call this an equilibrium reaction. Here's a weak base. If we started off with a fluoride by itself, from sodium fluoride, the sodium disappears, leaving the fluoride ion. Because this is our starting species, there's the base. Picks off the hydrogen from water, and then forms hydrogen fluoride. Now, it likes to change its mind, and it's going to give off the hydrogen back to the former water. Now it's a hydroxide, but it's going to give the hydrogen to the hydroxide, forming the water. Because it's going to give off the hydrogen, we call it a conjugate acid. So you'll notice on the product side, we like to use the word conjugate, and then we describe whether it's going to be a base or an acid. Now we have, whenever we mix together a weak acid and a weak base, and here is something very important to memorize, with the same conjugates, the same conjugates, the same conjugate pairs, we could create a buffer. Before I get into what a buffer is, let's figure out what the same conjugate is. Let's go over here. If I mix together hydrogen fluoride and sodium fluoride, you can notice they have part of the species it's the same. So they both share the same atom fluoride. So this portion is considered the same conjugate pairs. Let's go down to these two equilibrium reactions. There's hydrogen fluoride, there's the fluoride, and then here's the sodium fluoride. Notice they have the same conjugates. So what's my point? Whenever you stick together a weak acid and a weak base, and they share the same conjugates, there's going to be a third equilibrium reaction that occurs. And this equilibrium reaction resists pH changes. So even if you add in an acid or base, um, it doesn't like to change the overall pH of the solution, because this equilibrium will adjust itself to to offset any new acid or base that it's added in there. We use buffers all the time. The best place to find a buffer is in your human blood. Um, so there's a liquid portion of the blood called plasma, and it needs to be around 7.4. Why is that? Well, there are special proteins called hemoglobins, Hg for short, and they carry oxygen. So if you have really acidic blood, for example, then you kill the transporting oxygen hemoglobin proteins, and then you may suffer from loss of life. So it's important to maintain a specific pH in your blood. So we have put in a bunch of buffers inside your blood, and they maintain that pH of 7.4. So that way your blood pH won't change. Why would your blood change to begin with? Well, if you remembered, carbon dioxide, when it's exposed to water, it likes to form an acid called carbonic acid, H2CO3. It's one of the ones you now have to memorize. And that can acidify your blood. But the buffers in your blood help neutralize that carbonic acid. So you could get a whole bunch of carbon dioxide in your blood if you're breathing really heavily as you're studying for this upcoming exam and that can turn into carbonic acid, and that could lead to a slight case of death. So the buffers help prevent this and help neutralize that carbonic acid. So buffers are really, really important. We also use buffers in various solutions because they help maintain the pH. There's buffers inside your milk, and that helps maintain the pH of the milk, because if it becomes too acidic, then it spoils. Again, buffers are made up of a combination of the same conjugate pairs. NO2, NO2 minus. By the way, the NO2 minus, another way of writing it is with the counter ion sodium, so sodium nitrite. So you can see it written like this. But bottom line is, when you have a weak acid and weak base with the same conjugates, then you know you've created a buffer. Now buffers can be made for different pHs. You can have a buffer which maintains a neutral pH such as 7.4, or you can have a acidic buffer which maintains a very acidic environment. So let's go ahead and go back to this. Overall summary: if you have a strong acid, strong base, it's neutral. Strong acid and a weak base, well, because of 100% ionization of acid versus partial ionization of base, you'll have a lot more hydrogen ions, so it's going to be acidic. Strong base, 100% ionization, so and partial ionization of an acid, so it's going to be mostly basic. And then here we have our weak acid and weak bases. If they have the same conjugate pairs, such as sodium fluoride, hydrofluoric acid, it'll be a buffer. On the other hand, if you have different conjugate pairs, so let's say hydrofluoric acid and ammonia, ammonia is a weak base, hydrofluoric acid is a weak acid, but obviously they have different conjugates, then the pH varies. Basically, it gets more complicated. You have to do extra equilibrium math, which we're so not going to do. So let's go through these different questions, applying what we've just learned. Hydrochloric acid is a strong acid. And by the way, I'm just going to have you, it says on there neutral buffer, but because there's different types of buffers, I'm not going to have you, I'm not going to worry about that, so we'll just say buffer. So hydrochloric acid is a strong acid. Sodium hydroxide is a strong base. Based on this chart, then this is going to be neutral. Hydrochloric acid, strong acid. Sodium acetate, that's going to be a weak base. Therefore, this is going to be acidic. And I'll start to speed up now. Hydrofluoric acid is a weak acid. Lithium hydroxide is a strong base. This is going to be overall basic. Here we have, oh look, same conjugate pairs for a weak acid, weak base. This is going to be a buffer. By the way, I should write base here. Hydrofluoric acid, sodium fluoride, that's another buffer. And then hydrofluoric acid, sodium acetate, different conjugates even though they're both weak. And therefore this is going to be pH varies. Let's do the other ones. We have an acid and acid. Go figure. That's going to be acidic. Weak acid and a weak base. That's going to be pH varies because they have different conjugate pairs. And then a strong acid, strong base. This is going to be neutral. So make sure to practice those problems. So testing you on that. And now we're going to get into titrations. So this is the last of the big calculations in chemistry that you have to learn. It's one of the most important ones. You'll see it in a variety of different sciences, including chemistry, biology, microbiology. They love doing titrations. Let's go ahead and show you a video just to give you some context in this. So this is the setup for a titration experiment and creates the data for our titration calculations. First off, be sure to take a look at my cursor as I move it around, our little mouse cursor. So right now I'm moving it over the thing that looks blue. That's a special glassware called a burette, and it contains our base. I'm going to go ahead and move down. There is a beaker, and that beaker contains an acid. And we're going to be doing a neutralization reaction where we add in a base to an acid until it becomes neutral. Now, we have a pH meter that's attached to it. So, as proof that the beaker contains an acid, there's a pH of 1.0, which means it's extremely acidic. Now, as we add the base to the acid, we call this titrating. Titrating. So this is a titration experiment. And we're adding enough base to an acid in order to make it neutral. Now, using the pH meter as a reference point, we're going to watch it go all the way up to a pH of 7. Now, the burette has a special knob on there called a stopcock that, when open, it allows the base to feed into the acid. Now, let me go ahead and speed up a bit. So now we see the base going into the acid. When we add enough base into the acid where it's been neutralized, we call it the equivalence point. Now, watch how it, there we go. Now when the pH is 7, then we've added enough moles of our base so that it equals the moles of the acid at a pH of 7. So again, the equivalence point is when the moles of the base added in equal the moles of the acid, resulting in a neutral solution at pH of 7. This is a university level titration. On a community college budget, we may not be able to afford these fancy pH meters. So we have to add in a indicator. So these are liquid indicators. The one that we're going to be using is phenolphthalein. So we added in 1 or 2 drops into our previous acid solution, and we know that if it's acidic, it's going to be clear. If it's basic, it's going to be pink. We are purposely going to go 1 or 2 drops past the equivalence point, and that's how we know we've reached the end point. And that's when the end point is when the indicator changes color. And we're going to assume the end point equals the equivalence point. So let's go ahead and see this. And this is what actually happens in a real-life chemistry titration experiment. All that is required is 1 more drop, once you've reached the equivalence point, 1 more drop of base. Boom. That causes the pH change. Notice it's now a basic solution. And notice, because of the indicator phenolphthalein, it's now pink. So let's go ahead and see this all over again. There's our starting acid and base that we're going to add in. And then on the bottom, we have the amount of mils per second that is going to be added in. The cool thing about this burette is it's numbered, just like our graduated cylinders, so we know exactly how many mils are being put in. And as we add more base to the acid, you'll notice the pH changes. And then when the pH, when the base is added to the acid enough so that the moles of the base equal the moles of the acid, and the pH is 7, then we've reached the equivalence point. If we don't have a pH meter, then we had to have an indicator added, such as phenolphthalein, and so we purposely go 1 drop, maybe 2, past the equivalence point, activating the indicator to make it turn from its neutral form to its basic form. In this case, the indicator turns pink. Now we've reached the end point. So, titration is when we add in a specific amount of mils of our base, so we call it quantitative because we measure the quantities, of a solution of known concentration, in this case a known concentration of base, to an unknown concentration of acid. So the purpose of the titration is to allow us to figure out the unknown concentration of whatever's in the beaker using the known concentration, whatever in the burette, as a reference point. Now for this class, I'm going to make it pretty simple. We'll always assume the unknown concentration for this class is going to be an acid in the beaker. And the known concentration is going to be a base in the burette. Could we flip this? Could we have an unknown base and a known acid? Absolutely. But due to time constraints, we're just going to make it simple. And for this class, we'll assume unknown acid is in the beaker and a known base is in the burette. Now, having performed this experiment, I'm just going to fast forward again. We know how many mils of the known base was added in. In this case, about 50 mils of the known base was added in. So that's how much known base was added in. And if we have the molarity, we can go ahead and use our molarity as a conversion factor to go from mils of our basic solution using molarity to moles of our basic solution, and then set up a balanced equation to go from moles of base to moles of our acid. And that'll give us our known concentration of the acid. Let's go back to the slides and re-summarize what I just said using the slide as an example. Titration is used to measure the concentration of a acid solution, in this case it's the unknown, using a solution of base, which is the known. And this is the base is going to be the known concentration solution. The acid is going to be the unknown for this class, unknown concentration. So a measured volume of base is added to the acid solution. When all the acid has been neutralized, such as the pH equals 7, then we've reached the equivalence point. If you go one extra drop past the equivalence point, then you've reached what's called the end point. The end point. Now, we're going to assume for this class, to make our lives easier, even though we're cheating a little, cheater, we're going to assume that the end point is equal to the equivalence point. So the end point is equal to the equivalence point. Here is a paragraph describing a experiment that was done, and you're going to have to figure out the concentration of the unknown acid. In this case, the unknown concentration of acetic acid. What is the molarity of the unknown concentration of acetic acid? So the titration was already performed, and let me just go ahead and draw everything out. Here we have a beaker. The beaker originally contained 10 mils of our acetic acid. So there's our acetic acid. And then here is our burette. And we needed to add in roughly 37 mils of our base into our acid in order to neutralize it. So a 10 ml sample of acetic acid requires 37.55 mils of 0.233 molarity NaOH. So this is the molarity of the NaOH. So just like our molarity conversions from the previous packet that we studied, we're going to figure out what are the moles of the base. Now, based on the starting reactants, we can set up a balanced equation. Here's our balanced equation. It's both charge balanced, predicting the products, as well as equation balanced. And it's implied to be a 1-to-1 ratio. So we want the concentration of the acetic acid. And we have the concentration of the sodium hydroxide. So here's the plan of attack. You're going to go ahead and figure out, using molarity as a conversion factor, the concentration of the sodium hydroxide converted into moles. And we'll automatically assume that the moles of the base equal the moles of the acid based on the mole ratio from the balanced equation. Once we're in moles of acid, we then have to convert it into the proper concentration. For this example, we'll choose molarity, but I could have also just kept it in moles by itself, or I could have turned it into grams or milligrams or even molecules if given Avogadro's number or given the molar mass. But for this example, I'm just going to stick with molarity. So here is how we might set it up. There is our starting mils. Notice molarity has to be written as moles per liter when we turn it into a conversion factor, but we're starting off with mils. So you're going to have to do, and there's an implied conversion where 1 liter is equal to 1,000 mils. And what we've done is we've combined the molarity and the mils into one general conversion. this makes it easy for you, great. If you want to have this part separated, I also have other examples showing you the separation of it. But once we use molarity as a conversion factor, we now have the moles, and then we have to use the mole ratio taken from the balanced equation on the previous slide. And in this case, it's a 1-to-1 ratio. 1 mole of base equals 1 mole of acid. And notice how everything cross-cancels, leaving us the moles of our unknown concentration of our acid. Now we know what it is. And this is the whole purpose of titration, to figure out that unknown concentration of the acid. Now we need to go ahead and turn moles into molarity. So in the previous slide, we give you the starting sample of acid, happens to be 10 mils. So we're going to go ahead and convert moles into molarity. Notice mils needs to be, mils needs to be turned into liters. So I have to do an additional conversion. And now our final answer should be in moles per liter form, also known as molarity, and here is your final answer. You are so going to be tested on this titration experiments on the next quiz, exam, the final, post-final, your dreams, your nightmares, your future classes, random people on the street. It never dies. So let's go ahead and practice these titration calculations. I have embedded in the outline these type of calculations for you to practice with. Here is the outline right here. And if we scroll down, here are sample titration calculations. I've tried to make it nice and neat and pretty. So, consider the titration of a weak acid with sodium hydroxide. In this case, the weak acid is going to be acetic acid. So a 5 ml sample of a weak acid requires 47.5 mils of the 0.233 molarity sodium hydroxide. So again, in my starting beaker, I have 5.0 mils of my acetic acid. And then using a burette, in order to reach the equivalence point, aka the end point, because we use an indicator, I need to add in 47.55 mils of our known concentration of 0.233 molarity sodium hydroxide. And that will reach the equivalence point. Now, if I didn't provide one for you, and I give you your starting reactants, you have to go ahead and create a balanced equation as you see here. After balancing it, there's implied ones, so 1 mole of acid equals 1 mole of base. So there's our equality for the mole ratio we'll use. You have to turn molarity as a equality for a conversion factor. So there is my molarity as a conversion factor. Now in this example, what I went ahead and did was I put in a separate step the conversion of mils into liters. So that way it cross cancels out perfectly as you've been using this technique in your molarity slides. And the liters cancels out, moles is on top. Now that we have moles on top, let me go ahead and clean up some of that clutter. I can use the mole ratio from the balanced equation. And so the moles of the base equal the moles of the acid. It's a 1-to-1 ratio. And there is the moles of our weak acid, also known as acetic acid. Now, I need to go ahead and perform the reaction of the moles of the acid, acetic acid, over the liters of solution. The original liters was actually in mils, and that was 5.0. So we have to do a separate calculation, and I broke it down for you this time. I turned the mils into liters using the metric 1 liter to 1,000 mils conversion. And then I placed it on bottom. So it's moles divided by liters, and then here is the final molarity. Now let's get into everybody's favorite topic, sig figs. Let me clear out some of this clutter. Starting value has 4 sig figs. Same system, that's infinity sig figs, 3 sig figs for molarity as a conversion factor, and then infinity for the ratio. So final answer is rounded to 3 sig figs for moles. And then in a separate calculation, this is the original moles of solution of our acid. Infinity, 2 sig figs. Final answer is 2 sig figs. We then do a division, 3 sig figs on top, 2 sig figs on the bottom. So there's actually a mistake in this slide. It should actually be 2.2 molarity of acetic acid. And I'll probably change that on my actual outline that I post on the web. I don't spend a lot of time on the sig fig issues. I'm not going to trick you on the quiz or exams with improper sig figs for the multiple choice. If I were to give you any handwritten problem though, then it would have to be proper sig figs. So for example, a virtual lab where everything is handwritten in the virtual lab, then you'd have to write proper sig figs. For multiple choice questions, it's hard to do proper sig figs, so you'd have to go by your best sig fig guesstimates. Let's see other problems. Here is another titration reaction. Notice how it's worded just a little bit differently, but it's still the same type of titration setup. So make sure you practice with this format as well, with these type of paragraphs, and do the same type of titration calculation. Here's our starting reactants. First thing you do is you create your balanced equation, and you want to practice these. I have questions like these in the study handout, so make sure to practice these. It's already been balanced, so 1 mole of base equals 1 mole of acid. We want the unknown concentration of HCl. First thing we do is we turn molarity into a conversion factor. Now I could do divided by 1,000 mils, but I decided just to separate out into a separate step. 1 liter is 1,000 mils, so it cross cancels. There's the molarity as a conversion factor. And then here's the mole to mole ratio from the balanced equation. There's our moles. In a separate step, I converted mils into liters for the acid solution before it was titrated. And then it's moles of our HCl divided by liters of our HCl, and then there's your final molarity. So here is another problem. Notice after we do the balanced equation, it's 2 moles of HCl to 1 mole, or 1 implied 1 mole of calcium hydroxide. So for the coefficients, it's a 2 to 1 ratio. And that'll be important when we include our mole ratio with the 2 and the 1 here. Without this, then you'll have the incorrect answer. So make sure you have that balanced equation so you can figure out this part down here for the proper mole ratio. Everything else is the same. Actually, I made this a little bit easier because we started with liters instead of milliliters. So that's actually less steps. So we directly convert from liters to moles using molarity as a conversion factor, and then divide the moles of our HCl by the liters of the HCl solution, and then there is the final molarity. Now I mentioned there's other types of concentrations we could focus on. In this case, we can just focus on using grams and milligrams. So this does require a molar mass. FYI, there are 2 ways of saying the same thing. So another word for molar mass is equivalent weight. Again, another word for molar mass is equivalent weight. It's the same thing. So careful on that for future questions, because they may use the term molar mass, or they may use the term equivalent weight. Now we go ahead and we throw you a curveball. We have an unknown weak acid. Because we have an unknown weak acid, then I'm just going to go ahead and give you the information right here and say when it comes to the mole ratio, you can automatically assume it's a 1-to-1 ratio. So I'll give you some sort of hint letting you know what that mole ratio is. If I don't give you reactants to form a balanced equation, then I'll just let you know what the ratio is. Now, our initial setup is the same. We have to go ahead and start with mils of our known base solution, convert it to liters, use molarity as a conversion factor, use the 1-to-1 ratio as just implied. And now we have to use the molar mass. Now, you have to turn that into an equality. So 1 mole is equal to 179 grams. Moles goes on bottom, so that way it cross cancels, and that leaves grams on top. Now, I could have ended it there and just said grams of weak acid, but I wanted to be super tricky and say milligrams. So I had to do one additional conversion. And then here is your final mass of your weak acid in milligrams. Let's do sig figs. We have 3 sig figs here, infinity, 3 sig figs. By the way, it's implied to be 3 sig figs down below for the molarity as a conversion factor, infinite, 3 sig figs, implied to be 3 sig figs down below for the molar mass as a conversion factor, and then infinite. So it's rounded to 3 sig figs. Instead of grams, I could ask for molecules. In this case, it's unknown, so 1-to-1 ratio. The only difference between this and the previous problem is instead of using molar mass, we're going to use Avogadro's number. So 1 mole is equal to that famous number, 6.02 times 10 to the 23rd. Everything else is the same setup-wise, mils to liters. And then molarity is a conversion factor, so it cross-cancels, leaving the moles, 1-to-1 ratio. Moles of base equal moles of acid. But now that we're in moles of acid, then we can go ahead and place in the equality into a conversion factor. So moles goes on bottom because it cross-cancels, molecules goes on top, and there is your final answer with proper sig figs. 3 sig figs, infinity, 3 sig figs, infinity, 3 sig figs, ergo 3 sig figs. Now this last one is a little bit different, but we can use titration calculations to figure out the molar mass of an acid. So this is pretty cool, because once we know the molar mass, once we know the molar mass, we can go ahead and use a special table to look up the molar mass to figure out our unknown identity. So for example, if I had an unknown and its molar mass was 82.07 grams per mole, then looking at a special Merck index table which lists all molar masses and acids, that would match up with sulfurous acid, H2SO3. So this is a cool technique to figure out the molar mass of not only a known acid but an unknown acid, if you want to play detective and figure out what acid you're dealing with. Now, a couple things you need to know. We have to assume, in this case, it's a 1-to-1 ratio. If it isn't, then that makes things much more complicated. Conversely, what I could always do is just give you, instead of unknown weak acid, I could have changed this and given you the actual name of the acid, such as H2SO3. In which case, you would have to go ahead and do a charge balance product prediction. Producing water and sodium sulfite. And then you'd have to go ahead and balance out the equation. So in this case, there'd be a 2 here for sodium hydroxide, and then there'd be a 2 here for water. So given a equation balanced reaction that we just did based on the coefficients, then we would know that it would be a 1 mole of H2SO3 to 2 moles of sodium hydroxide. Now, I can then continue with the experiment, but then that's kind of lame because I can just look on Google what the molar mass is rather than doing the titration. But still, proof of concept. So let's go backwards in time and assume that we have an unknown acid. And let's also assume that we know that it's going to be a 1-to-1 ratio. So 1-to-1 ratio there. We're starting off with liters just to make our lives a little bit easier rather than mils. So molarity is a conversion factor. Everything cross cancels, leaving moles of our base. That cross cancels, leaving moles of our acid. Now that we have moles of the acid, let me get rid of some of this clutter. Now that we have moles of our acid, let's go through the definition of molar mass. Molar mass is grams of our substance divided by the moles of our substance. So if you were to sit there and look up oxygen, for example, and it says something like 15.99, that's actually 15.99 grams per 1 mole. So it's assumed that we already were able to measure out the grams of our sample right there. So there's our grams. And then here are the moles. And so you simply divide grams divided by moles, and then that gives you the molar mass, aka equivalent weight. So be sure to practice these type of problems. I've got a bunch of them in the study handout. And this concludes our acid-base titration component, as well as all of acids and bases part 2. Thank you.